Hello once again, Algebra 2 students at Verdugo. I'm doing this video now for lesson 1 on graphing cube root functions. Okay, so we're going to start graphing cube root functions. We just did graphing square root functions. So if you remember, square root, so like a square root of 25 would be 5. The principal square root would be 5. The square root of 81 is 9. The square root of 1 is 1, and yada, yada, yada. Now what we're doing is we're doing cube root functions. Just a quick reminder what a cube root is. For example, the cube root of 8. That has a perfect cube. And the cube root of 8 is 2. The reason I know that is because 8 is 2 times 2 times 2. 2 multiplied by itself 3 times. So what else has a perfect cube? Let's think about it. Cube root of 1. 1 has a perfect cube, and that would be 1. Because then that would be 1 times 1 times 1. Perfect. What else has a perfect cube? Another common one you'll see is 7. And that would be 3. And it would be 3 because we have 3 times 3 times 3. But the interesting with cube root, so going back to square root for a second, if I say square root of 25, you say 5. Great. But if I say square root of negative 25, it doesn't have a real solution because it's not negative 5 times negative 5. It is also not 5 times 5. Okay, that's when you get into imaginary numbers, which doesn't concern us right now for our graphing. Okay, however, we don't have a solution. However, for cube roots, you can actually have a cube root of a negative 8 because something does multiply by itself 3 times to give us negative 8. That would be negative 2. Let's try it out. Let's make sure it works. Negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. That works out. So the cube root of a negative number is also going to be its negative. So the cube root of negative 1 would be negative 1 because it's negative 1 times negative 1 times negative 1. The cube root of negative 27 would be negative 3 because it's negative 3 times negative 3 times negative 3, and so on and so on. So we can keep going with this, but those are just some of the basic cube roots you're going to see. Cube root of 0 is also an easy one. Cube root of 0 is just 0. 0 times 0 times 0. Okay, so with that in mind, let's jump into it now. As with all functions that we start with, we're going to go with the parent, the OG, the original graph. So that's going to look like this. F of x equals cube root of x. Notice I'm putting a cube root, a third root here, okay? If it's a square root, traditionally they don't put a 2 there, they just leave it alone, okay? That when there's nothing there, it means square root. But since it's not a square root, I don't want square root, I want a cube root, I'm going to put that. If I wanted a 4th root, I'll put that. If I wanted a 7th root, I put that, so on and so on. Okay, but for now, we're just doing cube root, okay? So let's do this. Just like always, what do we need? We need our x-intercept. We need our y-intercept. And let's kind of mess around after that to see what else. Find out what the graph looks like. So I'm just going to make a quick grid right here. Okay, first let's do x-intercept. So for x-intercept, we need to make the y 0. We need to make the y 0. So I'm going to make the y 0. Okay, so now that we have that, I want the x. I want to know what's going on here. Well, if you remember in square root, if I have a square root of x, in order to cancel out the square root, we square the entire quantity, and it cancels that entire thing out. Well, same thing here, except this time we're not going to square it, we're going to cube it, because that's a cube. So I'm going to cube this entire thing to the power of 3. But what I do to one side, I must do to the other. So I'm going to do that thing too. So now we're going to end up with 0 to the power of 3, which is 0, is equal to, well, the cube root and the cube cancel each other out. So I'm just left with x. There you go. Found it. Our x-intercept is 0, 0. And that's when the alarm bell should go off, because you're seeing an x-intercept of 0, 0. which has to mean just one more thing. If this graph touches the x-axis at 0, 0, well, guess what? It's also touching the y-axis at 0, 0. That's the only point where they both meet. So I know right now the y-intercept is going to be 0, 0. But just for fun, let's do it. Let's make sure that is the case. Let's do it to make sure that's the case. So the y-intercept, we're going to make the x 0 this time. So let's make the x 0. So y is equal to, you know what, let me just write it x. I wrote it here. Y is equal to the cube root of 0. Well, what multiplies with itself 3 times to give us 0? That's going to be 0. So y equals 0. Yeah, that seemed about right. We knew it was going to be at 0, 0. Great. Doesn't tell me what to do, though. I don't know what this looks like. I don't know what a cube root graph looks like. You know you know, if I were to do, well, let's not get to that just yet. I want to actually experiment with it and find out. But I wouldn't do this every time. I'm just going to do this for this case just because I don't know what this looks like. I'm approaching this just like you. I don't know what this looks like. So I'm going to plug in the number here for x. Not 0. We already have 0, 0. I'm going to plug in another really easy number. Let's think of a really easy number that we know the cube root of. Again, I'm not going to put in 5. That's a dumb value to put because cube root of 5, sure, it exists, but I'm not going to sit here and start doing decimals, okay? Not doing that. So let's put a cube root that we know. For example, 1. We know 1. So let's do this mental math here. I'm going to plug in a 1 here. So f of x, or y, is equal to the cube root of 1. What's the cube root of 1? 1. Cool, got it. 1, 1. Let's try another value now. What's another one that we know? And we did this just a while ago. I was showing you the perfect cubes. 8. 8 is a good one because there is a cube root of 8, a perfect cube root of 8. And that is going to be 2. So I got 8, 2. 1, 2, 3, 4, 5, 6, 7, 8, and 2. Okay, I mean, it's not perfect, doesn't fit, you know, but just do the best you can. Now, right now that looks like, oh yeah, look, that seems to be done, but I'm forgetting something here. Remember what I said? I said for cube roots, you can put negatives in here. You can find the cube root of a negative, absolutely fine. So we did 1 and 8. Let's do negative 1 and negative 8. Let's try those two. Let's try negative 1 first. The cube root of negative 1 is going to be negative 1. Because negative 1 times negative 1 times negative 1. So that's going to be, the cube root of negative 1 is negative 1. Let's do that. Negative 1, negative 1. Good. We graphed that one too. Let's plot this last point. So negative 8, the cube root of negative 8 is going to be, let's see, that's negative 2 times negative 2 times negative 2. Yes. So it's negative 2. So negative 8, 1, 2, 3, 4, 5, 6, 7, 8, and negative 2. So somewhere here. And if you look at it, it's looking like this right here is copied up here. That's what it kind of looks like. If we were to graph this out, it would look something like this. Okay, it's not a very, I didn't do a very good job, but you guys get the point. It would look something like that. And there's something I want to point out here. Yes, this is not a parabola. Parabola traditionally has a vertex. Parabolas have vertices, sideways parabola, whatever. They have a vertex. I don't have a vertex here, but I do have a very important point right here at 0, 0. So what's happening, if you notice, I like to call this like a pivot point, okay? It's actually called the point of inflection. What's happening is, if you notice the way this is going right here, it's curving, it's curving, it's curving, and then it starts curving this way. It kind of changes directions and curves this way. So in a way, it's not perfectly symmetrical, but like, well, in a way it is, yeah. So this right here, it's inflected here. So what we call that here is a point of inflection. So if I knew this was at 1, 1, guess what? This is at negative 1, negative 1. 8, 2, negative 8, negative 2. We were kind of able to figure that out. You know, if I was actually graphing this, just sketching this graph, I wouldn't go through all this trouble. I would just go, done. But just to let you know, that's what's called the point of inflection. So if we ask you guys, what is the inflection point, or the point of inflection, kind of similar to vertex, what we would say is 0, 0. That's why the parent function is so easy. It's just very straightforward. Okay, now I want to go with a couple more things. So I'm going to be erasing this in just a second. So take a good look at it. Okay, I want to go over one more thing, I should say, not a couple more things, just one more thing. And that is going to be the domain and range. That's actually very simple on this graph, the domain and range. Again, domain, just a quick reminder. Those are our x values. And then range, those are our y values. Okay, so domain left to right. X values go left to right. So think about this. Would this go forever left? Yes, it would. That is negative infinity with parentheses. Would this go forever right? Yes, it would. Positive infinity with parentheses. Let's talk about range now. Now, range is a little bit different. Students get caught up in this. It may look like, oh, this doesn't go forever down, it stops. It actually doesn't stop. If I were to continue this, look what happens. If I were to continue this, it's not, yes, it's going left, that's obvious, but it's also actually going down, 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 down. So is it going to go forever down? Yeah, slowly, but it will go forever down. That is a negative infinity. And same thing on this end, it will go forever up too. It's going forever right and forever up. So this would be positive infinity. So the domain and range on cube root functions is actually pretty straightforward. So that's the first video. The second video, we're actually going to take this, not the parent function, we're actually going to, I'm not going to give you the parent function, I'm going to manipulate that a little bit, shift this around a little bit, and it'll be the same deal, just a little bit more complex, okay? See you in video 2.